There's a visual way to gain some insight into these antidifferentiation problems.
So that visual method goes by the name of slope fields.
So what's a slope field?
The idea is that I start with some function, like here's an example, a function x squared minus x, but instead of just graphing the function like I normally do, here I'm graphing the function's values. I make a graph, but the thing that I'm graphing is little tiny line segments of that given slope, right? So instead of plotting a value at some height, I draw little tiny line segments with that slope. Now you can see in this example, if you plug in 0 or 1 into this function, the output 0. And in this slope field, if you look at a point whose x value is 0 or whose x value is 1, there I'm plotting just horizontal lines, lines of slope 0. Over here I've got very high slope, and over here I've got very high slope. And that just reflects the fact that this function's value is very high when x is negative and when x is positive. And in between here I've got just a little tiny region where the lines are pointing down, right, where the slope of these little line segments is negative. And of course that's because there's a little tiny region here where this function's value is negative.
Well, let's look at a specific example.
Well, here's a specific example. Function big F of x equals x times cosine x.
Now I can draw the slope field for this example.
Well, in that case, here's the slope field that I get.
Imagine that I had an antiderivative, a function little f, whose derivative was big F.
That is, suppose I had some function little f whose derivative was big F. Now, remember, the slope field is drawn so that all these little line segments have slope equal to the value of big F. So I could use this slope field to try to draw a picture, the graph of my function f, right? Let's suppose that my function maybe starts here, and then I could try to follow the slope field along and try to use the information in the slope field to try to draw a picture of what my function f must look like.
So these slope fields let you see the antiderivative, right? If you follow the slope field, you're tracing out a function whose derivative is given by the slope field.
And we can find this antiderivative, right? We're trying to antidifferentiate x cosine x. Well, our first guess might be x sine x. I mean, that's a reasonable guess because differentiating sine would give me the cosine, right? But what happens if I actually differentiate this product? Well, that's the sort of thing that I do with the product rule, which is x times the derivative, which is cosine x. So that's looking good. But it's plus the derivative of the first, which is 1, times the second, which is sine x. So the antiderivative of x cosine x isn't just x sine x because I've got this pesky additional sine x term. But I also know that the derivative of cosine is minus sine. So if I add these things together, right, if I add them together, what's the derivative of x sine x plus cosine x? Well, it's these two things added together, but that's x cosine x, which is good, plus sine x minus sine x. So it's just x cosine x. So that means the general antiderivative of x cosine x is x sine x plus cosine x plus some constant c. And yeah, we can see this in the graph. So here I've graphed x sine x plus cosine x, and you can see that it's really moving in the direction of the slope field, which makes sense because the slope field is coming from x cosine x, which is the derivative of this thing. And I drew the slope field by drawing little tiny line segments whose slope is x cosine x. So since this thing differentiates to x cosine x, this thing is really moving along the slope field.
The slope field picture also gives you some insight into how the plus c really works.
What is the plus c really accomplishing, right? It's moving the graph up and down. And if you start with, say x sine x plus cosine x, and then you slide that graph up and down, it's still following the slope field, right? It's still an antiderivative for x cosine x.